Hello everyone. Today I am here to tell you something about generalized mean value theorems. And in this tutorial we are going to learn one of the most important mean value theorems, which is also called generalized mean value theorem. That is known as Taylor's theorem with Lagrange's remainder. And before this, previous to this topic, we have learned in prior classes. We have learned two mean value theorems. One is Lagrange's mean value theorem, which is also known as first mean value theorem, and next is Cauchy's mean value theorem, which is also known as generalized mean value theorem. And here also we have got term generalized mean value theorem, and Cauchy's theorem is also known as generalized mean value theorem. But here this Lagrange's mean value theorem and Cauchy's mean value theorem are the mean value theorems of first order. You know, these theorems use only first order derivative of the given function fx. So these are first order mean value theorems. And here we are going to learn about generalized mean value theorems of nth order here. Right? This is generalized mean value theorem of nth order. Means here we'll be using nth order derivative of a given function. Okay, then what you have learned in previous mean value theorem is that both of these theorems use Rolle's theorem, and Rolle's theorems are being fundamental for all mean value theorems, and we'll be using here too Rolle's theorem to prove this theorem as well. Okay, then in Lagrange's mean value theorem, what is the statement? We had got two statements here. One was in terms of c, f dash of c equals to f of b minus f of a upon b minus a. And next, if we put b equal to a plus h, then we got here another statement, f of a plus h equal to f of a, then plus h f dash of a plus theta is provided 0 is less than theta is less than 1. These two forms we learned in Lagrange's mean value theorem. And actually this C was the point between the points A and B in the given interval. And the first one expression tells about the slope of the tangent at point C to the curve fx. It talks about that one. And second one, if you see, the statement is little different from first one. This says that and here f of x is defined in the interval a to a plus h, and here the value of f of x at point a plus h is approximated by the value of f at point a, and there is a point, let's say here a plus theta h. This is the point here. A plus theta h means the distance from here to here is theta h, and there is f dash of a plus theta h means the value of its derivative at points a plus theta h. F dash of a plus theta h means value of fx at value of the derivative of fx at point a plus theta h has been used to approximate the value of the function fx at point a plus h. So it looks like similar to expansion of f of a plus h in terms of fa. Looks like that. And we are using the same concept here in series expansion of the function. And under this series expansion of this function, we will be learning first Taylor series expansion, and after learning Taylor series expansion, we'll be learning about Maclaurin series expansion. So Maclaurin series expansion will derive from the relation of Taylor series expansion. So we are here first to learn about Taylor series expansion in finite form first, and or this is also known as Taylor theorems with Lagrange's remainder. And one thing you need to note that Taylor's theorem have different forms, right? Different forms. There are different forms of Taylor's theorem, but here we will be learning only two forms. One, Taylor's theorem with Lagrange's remainder, and next is Taylor theorems with Cauchy's remainder. Means Lagrange's form of remainder is one theorem, and next is Cauchy's form of remainder. And here I am going to show the statement and detailed proof of this theorem, Taylor's theorem with Lagrange's remainder. And after that, we will be doing Taylor's theorem with Cauchy's form of remainder. So let's first go through the proof. Now, first we'll discuss about the proof strategy of this theorem. And to prove this theorem, we use the same strategy as we did in earlier mean value theorems of first orders. What we did in Lagrange's mean value theorem, if you have remembered, in Lagrange's mean value theorem, what we did there is we are given a function f of x, define an interval AB, and then to prove Lagrange's mean value theorem, we use the second line that joins the point A comma FA and B comma FB. So equation of the straight line, second line will give a function y, and we have been given the function fx. So there what we did, we wrote the difference of these two functions fx and y to get another function on the same domain, on the same interval, defined at the same interval. So we use the same strategy. Here we have got a function and many other functions. Many other functions means the derivatives of these same functions. Okay. So first of all, what's the statement of the theorem? Let's go to the statement. First one is if a function fx defined and closed interval AB is such that fn minus 1x is continuous on closed interval AB, means its derivative up to n order, means fx to fn minus 1x are continuous on closed interval AB. When fnx is differentiable on open interval, its nth order derivative exists on open interval AB, then there exists a number c in AB such that value of f at b, f of b equal to f of a plus b minus a f dash a plus b minus a whole square by 2 factorial f double dash a plus b minus a whole cube upon 3 factorial f triple dash a plus the other b minus a whole power n minus 1 factorial fn minus 1a plus the last term is b minus a whole power n upon n factorial fn of c is here. Okay, so here actually we need to find the number c here, isn't it? Because a and b we have been given the interval. Actually we need to find the point c here. And then, as I told you, proof strategy is similar to Lagrange's mean value theorem or Cauchy's mean value theorem, whatever we say. But difference is that here are a number of functions fx, f dash x, f double dash x up to fn minus 1x continuous function has been given. So we'll be using functions from fx to fn minus 1x to define a new function hx or phi x, whatever you say, you can name yourself. So first we'll consider a function. Let's consider a function. Consider a function phi of x defined on AB, defined on closed interval AB h phi of x. Now to define this function, what we do here is we'll just replace a by x in the statement that we are going to prove here. Right? Means what do you write here? F of x plus b minus x f dash of x plus b minus x whole square by 2 factorial f double dash of x plus or you can do plus b minus x whole power n minus 1 upon n minus 1 factorial fn minus 1 of x plus the last time we write b minus x whole power n upon n factorial times a, okay, a where a is a constant to be determined so that phi of a equals phi of b. Now look here. We define a function phi x by using the function fx, f dash x, a double dash x till f n minus 1 x and other polynomial functions. You can see b minus x whole square, b minus x whole power n minus 1, b minus x whole power n. The other polynomial functions. We define a new function phi of x, and it's defined in the same interval ab, means x belongs to ab, and here we use a constant a. And we told that we need this a is such a constant, or we need to find a in such a way that the value of phi at point a and b means phi a will be equal to phi b. Means whenever a satisfies this condition, then expression for phi x will be this one. It means, so here we are adding one condition to choose this constant a, phi of a equal to phi of b. And actually what we are doing, you might have understand also, or you might have guessed also, we have formed phi x so that this will be satisfying Rolle's theorem. You can see clearly how. The first condition, you can see phi x is defined in terms of fx, f dash x, fn minus 1 x and other polynomial functions, and we have been given up to fn minus 1 x are continuous functions, up to fn minus 1 x are continuous and closed interval ab. So here are all the sums. That means this is the sum of the continuous functions. Each and every terms are continuous on closed interval ab. So phi x is continuous and closed interval ab, we can say very clearly. And next we have been given that the derivatives, then till nth order derivatives exist on open interval ab. So here we have used up to n minus 1 order derivative of the function, isn't it? That means fx, f dash x, f double dash x, fn minus 1 x, all of them are derivable on open interval ab, and these other polynomial functions are what called derivable on open interval ab. That's why phi x is also derivable on open interval ab, means phi x is differentiable on open interval ab. And third condition, we have chosen a in such a way that phi a will be equal to phi b, isn't it? We have chosen phi a equal to phi b to find a, or we need to find a satisfying this condition. So what happens when phi a equal to phi b? Let's see. Means how to find a, no? Then whenever we take phi a equal to phi b, then we will get value of a. It means that. So what happens if we do phi a? What happens if we do phi b here in this expression? Let's say this is expression 1. Say this is expression 1. Okay. And then here, if you put x equal to b, what happens? It is very clear. If you put x equal to b, except first term will be fb, other term will be 0. b minus b, b minus b, b minus the last term. So you can see from 1 you can see phi of b equals f of b. And what will be the value of phi of a? Isn't it? And phi of a will be equal to f of a plus b minus a, f dash of a plus b minus a whole square by 2 factorial f double dash of a plus dot plus b minus a whole power n minus 1 upon n minus 1 factorial fn minus 1 of a plus b minus a whole power n upon n factorial times a. And now we have to use phi a equal to phi b. Whenever you use phi a equal to phi b means in place of phi a you have to prove fb, means then if you combine these two conditions, no? If you combine these two conditions you will get a new expression, because we are choosing a such that phi a equal to phi b, means we have to equate phi a and phi b to get value a. So what happens? Therefore phi a equal to phi b implies phi a equal to phi b implies f of b equals just put here phi a equal to phi b and phi b equal to fb, means phi a will be equal to fb. F of b equal to f of a plus b minus a f dash of a plus b minus a whole square upon 2 factorial f double dash of a plus b minus a whole cube by 3 factorial f triple dash of a plus that b minus a whole power n minus 1 upon n minus 1 factorial f of n minus 1 of a plus b minus a whole power n upon n factorial f n in place of n factorial a only will be there. Yes, a will be here. So let's say this expression 2. This is the expression 2. Okay, now we are getting almost the statement of the theorem, but still value of a is undetermined. Means whatever value we get from this statement 2, whatever value of a we get from this statement 2, isn't it? For that value of a, phi x will be satisfying Rolle's theorem. Isn't it? Phi x will be satisfying Rolle's theorem. Now let's write about the Rolle's theorem. Okay. Then number 1, we have been given that all these functions, since f of x, f dash of x, f double dash of x, that f n minus 1 of x are continuous on closed interval a b. We have been given this one. So phi x is continuous on closed interval AB. I told you already, phi x is defined in terms of fx to fn minus 1x and other polynomial function b minus x welfare has been used, which are continuous everywhere. So fx to fn minus 1x are already continuous, that is given by the hypothesis, and polynomial functions are being continuous. Phi x is also continuous on closed interval AB. And second one, we have been given f dash x, since dash x, f double dash x, f triple dash x, up to fn x we have been given, but we don't use fn x here. We use here only up to fn minus 1x. fn minus 1x are differentiable or derivable. Derivable on open interval AB. So phi x is also differentiable. So phi x is derivable or differentiable on open interval AB. And now let's go through third condition. Third condition is phi a equal to phi b. Then what we have told that we have chosen a constant a in our assumption, and we are going to determine constant a in such a way that phi a equal to phi b. And we have done here phi equal to phi b also. And what we get? We got a value of a also. Isn't it? So for this value of a given by this expression 2, isn't it? This phi of x will be satisfying phi a equal to phi b. Isn't it? So in number 3 you can see for the value of a, or value of constant, let's say constant a given by expression 2, phi a will be equal to phi b as well, isn't it? It means phi of x satisfies all three properties or three hypotheses of rule theorems. Therefore, phi of x fulfills all hypotheses of Rolle's theorem So there exists a number, means at least one number, but I'm writing a number, C in open interval AB, such that phi dash of C equals 0. Let's say this condition 3. 1, 2, 3, yes. How about third condition? Okay, now we have to impose this phi dash of C equal to 0. And but to use this condition phi dash of C equal to 0, we need phi dash x at first. So we'll first find phi dash x from the expression 1. So from 1 you can write phi dash x. Then what happens here? Let's see. Then from 1 phi dash of x, let's write, what will you get? Equal to, now let's do term by term differentiation here. Let's do differentiation of first term will be f dash of x plus, now differentiation of second term, let's go through. And here are two functions of x, one is b minus x and is f dash of x. First I'll do differentiation of f dash of x. So I'll write here plus b minus x, derivative of f dash x will be f double dash of x. Now I need to differentiate b minus x, means which derivative will be minus 1. So f dash of x. Then you can understand. And the second term produces two terms after differentiation by using product formula. First I differentiated f dash x, so f double dash x. And secondly I differentiated b minus x, so derivative minus 1, so f dash of x as it is. Now go to third term. In third term plus, here I first differentiate f double dash x, means b minus x whole square divided by 2 factorial. A derivative of f double dash x will be f triple dash of x. Now I need to differentiate b minus x whole square by 2 factorial. As you know, if you differentiate b minus x whole square, what will you get? You will get 2 times b minus x to the power 1. And again you have to differentiate b minus x, means you will get minus 1, and divided by 2 is there, then 2 is cancelled there. So what will you get here? You will get minus in between, minus b minus x f double dash x, and next let's go to second last term now. Now let's go to second last term. this one, the term that contains fn minus 1x, okay, here to this term. First I'll differentiate fn minus 1x. The derivative of fn minus 1x will be what will be there? Derivative of fn minus 1x means it will increase by 1, means fn x. So what will be here? B minus x whole power n minus 1 upon n minus 1 factorial fn of x. And now next term means we have to differentiate b minus x whole power n minus 1. I'll write here, okay. Then what will you get? The next term, you'll get, okay, I'll write here, plus now next term means I have to differentiate this b minus x whole power n minus 1, okay. Now what will you get here? N minus 1, then b minus x whole power n minus 2 upon n minus 1 factorial, but still we have to differentiate b minus x, so you will get here minus in front, and f of n minus 1x as it is. And now let's differentiate last term. Last term means we have got this b minus x whole power n upon n factorial, means we need to differentiate only one term here. Its derivative will be n b minus x whole power n minus 1 upon n factorial times a. A is constant, so we are not using here product formula. So we got this phi dash x. And now let's observe here. You have to inspect through it. Here most of the terms are being cancelled here. How? Let's see. Let's watch this f dash x and minus f dash. These two terms have been cancelled each other. Then plus b minus x f double dash x minus b minus x f double dash x have been cancelled here, isn't it? Similarly, isn't it, if you have found the derivative of third term here, and you'll get after this term also would be cancelled. The term that comes immediately after this one, I mean this term also will be cancelled, isn't it? So here only two terms will remain here actually. That is the last term and third last term, and this term also will be cancelled with the terms that comes previous to this term, isn't it? So you'll have here phi dash x like this. Phi dash of x equals to, you'll get b minus x whole power n minus 1 upon n minus 1 factorial f n of x, and the last term is plus. Now you can see here n upon n minus 1 factorial means what? N upon n minus 1 factorial means n upon n factorial. N upon n factorial means n upon n times n minus 1 factorial means n cancel, means 1 upon n minus factorial, means you can write this way: b minus x whole power n minus 1 upon n minus 1 factorials times a, means what will you get here? B minus x whole power n minus 1 upon n minus 1 factorial, you take common outside, and what remained here? Fn of x plus, sorry, here I did one mistake. What is it? I did differentiation of b minus x, means here will come sign minus, okay, sorry for that. Okay, will be minus, okay, fn x minus a. Okay, then we found phi dash of x. Then what is the phi dash of c then? Isn't it? Now we'll use that. Okay, I'll not be drawing this one. Okay, I'm going to keep this to use this later on. Okay, and after this, therefore phi dash of c equals, just put your value, b minus c whole power n minus 1 upon n minus 1 factorial here fn of c minus a you'll get here. Now we'll be using phi dash of c equal to 0 from 3. Let's use this 3. If we use this 3, you'll get 0 equal to b minus c n minus 1 upon n minus 1 factorial fn of c minus a. Okay, then we have chosen c in such a way that our c lies between open interval ab, so b and c can be equal. They are never equal, so b minus c is never equal to 0. So you can conclude that this term never vanishes. This is never equal to 0. Means what should be equal to 0? fn of c minus a must be equals to 0. Means you'll get a equals fn of c. We got value of a. Now we substitute this value of a in the expression that we have already derived by using phi equal to phi b here in expression 2. So therefore from expression 2 the substitute values, we get f of b equal to f of a plus b minus a f dash of a plus b minus a whole square by 2 factorial f double dash of a plus plus b minus a whole power n minus 1 upon n minus 1 factorial fn minus 1 of a plus b minus a whole power n upon n factorial. In place of a, you just put value of a means f and c, and which is the required result that we have to prove. Hence the theorem is proved this way. So this is the statement of the Taylor's theorem in finite form. It is finite form because you can see here are only n plus 1 terms. There are only n plus 1 terms. And here you can see the last term has different form than other one, isn't it? And it's note number 1, let's say. The last term b minus a whole power n upon n factorial fn of c is called the Lagrange's remainder. Lagrange's remainder and is denoted by Rn, means remainder after n terms. Okay, and you can see there are exactly n terms just before, means fa to fn minus 1. Okay, there are exactly n terms just before this remainder term. So this f of b contains two parts here. One from fa to fn minus 1a, you can see the one part, isn't it? And you can see here this b minus a whole power n minus 1. And probably this is n minus 1 degree polynomial, isn't it? This is the functional value fn minus 1 if I give some value. B minus a whole power n minus 1 is a polynomial. So you can see here that the function f of b or the value f of b can be expressed in terms of the sum of a polynomial here in first part that contains n terms and the remainder. So what can we share is that also right hand side, if you see there, isn't it? The right hand side, if you see there, the sum of first, how many terms are there? N terms. Sum of first n terms, isn't it? That means fa to b minus a whole power n minus 1 to n minus factorial of fn minus 1a, isn't it? N terms is denoted by Pn, just like Rn we do, isn't it? Pn and is called Taylor's polynomial. Taylor's polynomial. Therefore, what can we do here? Therefore, f of b can be written as Pn plus Rn, isn't it? Pn plus Rn. And similarly, next one is, one important thing what Taylor's theorem tells us is that next one is number 2. Taylor's theorem tells that f can be approximated. That means you say f of b is the value of fx at b, no? So f can be approximated. How it can be approximated? Approximated by a polynomial of degree n minus 1 here. By a polynomial of degree n minus 1, isn't it? And which error of approximation will be given by this remainder, isn't it? Approximated by a polynomial of degree n minus 1 if it has derivative of order n, isn't it? If it has continuous derivative of order n, or simply you can say derivative of order n, it has derivative of order n, and the remainder terms after n terms, that means, and the remainder Rn is the error made by this approximation, or the remainder Rn gives or represents the error made by this approximation. It's the second fact. And third fact about this theorem is that if you defined f of x in the interval a to a plus h, that means if you put b equal to a plus h, that means b minus a equal to h. That means if you take height of the interval, isn't it? Height of the interval, that means a to b. This is the height of the interval, means we just subtract b minus a, h, isn't it? Height of the interval to be taken is h. Then we can restate the theorem in another way. That means in place of b, there will come a plus h, and here in f of a, in place of b minus a, write h. Here h square by 2 factorial, there hn minus 1 and 1 factorial, isn't it? And here hn upon n factorial. But in place of c, isn't it, there will be, write another expression, means, look here, in place of c, what will be there? In place of c means at first we have chosen c in this way. There is some number c between a and b. But if we take height of the interval to be h here, isn't it? from A to B, then what will be the length of the interval from A to C? Means it is certainly less than h. Means we have to reduce, means we have to use a multiplier, isn't it? We have to use a multiplier, but that multiplier should be between 0 and 1, and here that is to be that is considered to be theta. Means what you see here, if we take height of the interval to be h, there is a number theta between 0 and 1, so that c will be equal to a plus theta as well, right? Means height will consider from A to C will be theta times h. For example, if h equal to suppose 5, isn't it? And if suppose A to C, let's put here number, some number, let's put here 0, it is 6, means height will be 6 here, height of the interval, okay? And suppose we got a number C as 4, suppose C equal to 4 we got, isn't it? Then distance from theta to C is 4, we know already, isn't it? So but we have to express that in terms of 6. Now what should you multiply 6 to get 4? Means probably 2 by 3, isn't it? 2 by 3. So this is the number between 0 and 1. So here theta will be 2 by 3. So if you write here A and B, if height is h, if this is C, then the distance from A to this point C will be theta h. So C will be equal to A plus theta h, isn't it? So in place of C, we will be replacing A plus theta h. We will be writing A plus theta h. Okay. If we put B equal to A plus h or B minus A equal to h, whatever you see, then Taylor's theorem, above theorem can be stated, can be restated is if f of x defined on A to A plus h is such that number 1 fn minus 1x is continuous on closed interval A to A plus h. Number 2, fn of x is differentiable on open interval A to A plus h. Then there exists a number theta in 0 to 1 or in open interval 0 1 such that, now in place of f of b we'll be writing f of a plus h equal to f of a plus, there was b minus a, then here will be h f dash of a plus b minus a whole square. We had got like this, no? B minus a square upon 2 factorial f dot dash a we had got, no? So in this place here will be h square by 2 factorial, h square by 2 factorial f double dash of a plus h cube by 3 factorial f triple dash of a plus h n minus 1 upon n minus 1 factorial fn minus 1 of a, and the last term is plus h n upon n factorial fn of c means a plus theta h, and this is again the Lagrange's remainder. Get it? This is also Lagrange's remainder in this form. When the function is defined on a to a plus h, the Lagrange's remainder will take this form. Okay. And next, until now, what we did, we took interval once. At first, we took interval a to b. Then we found the expansion of f of b. And secondly, we took the interval a to a plus h, we found expansion f of a plus h, then about x equal to a. And now next, what can we do? Next, you can take a to x. Suppose left end point is a, right end point is some variable x, isn't it? Then what happens? What forms does this Taylor's theorem take? Let's see. Now another form of Taylor's theorem or Taylor's series, and next number form, another expression, for Taylor's theorem can be obtained by putting b equals to x, b equals to x, and b equal to x in the statement f of b equal to f of a plus b minus a, f dash of a plus b minus a whole square by 2 factorial f dot dash of a plus b minus a whole power n minus 1 upon n minus 1 factorial fn minus 1 of a plus b minus a whole power n upon n factorial fn of c. In this statement, we will replace b by x to get, which takes the form f of x equal to f of a plus x minus a, f dash of a plus x minus a whole square upon 2 factorial f double dash of x plus x minus a whole power n minus 1 factorial fn minus 1 of a, and at last x minus a whole power n upon, I'll write the last terms below it, okay? And the last term is b minus a whole power n means x minus a whole power n upon n factorial fn. In place of c, what will be there? In place of c, actually we have got c. In place of c will be equal to a plus theta h, isn't it? So here we'll write a plus theta h means x minus a will be there, because height of the interval, we have taken interval a to x, b means, isn't it? There will be a plus theta times x minus a. Okay, we'll get this kind of expression where theta is where 0 is less than theta is less than 1. Means if you put b equal to x in the statement of this Taylor's theorem, which is defined on closed interval ab, we'll get this statement of expansion of fx in the closed interval a to x, isn't it? And this is called expansion of the function fx in the neighborhood of x equal to a, and it is called the expansion of function fx in the neighborhood of point x equal to a. Okay, this is all about the Taylor's theorem with Lagrange's form of remainder. So here we learned three forms of Lagrange's form of remainder. One was Rn equal to b minus a whole power n upon n factor fn of c, where c belongs to c belongs to open interval a to b. And next one was hn upon n factorial fn a plus theta, where theta lies in the open interval 0 to 1. And next one, but be careful that here the function fx is defined in the closed interval ab. Here the function f is defined on the closed interval a to a plus h, and when the fx is defined on the closed interval a to x, at that time remainder term will be x minus a whole power n upon n factorial fn of theta plus a plus theta x minus a. This will be in the expansion of fx about x equal to a, and mainly we use this one, okay, this one as Lagrange's remainder for Taylor's theorem. Okay, thank you. If you have any confusions, then you may ask me in online class, but go through this tutorial and repeat it and try to understand, and wherever you have good confusions, I'll try to clear you in our usual classes. Okay, thank you.